Okay, so welcome everyone to this new episode of EagleFly The Experimental Debugger. Today we will continue making this awesome debugger, and if you'd like to follow along, please don't hesitate and be welcome. Today we will continue making this assembler. So yeah, if you have any questions, post them on Twitter or YouTube or on Handmade Network. I have a post right there that you can post your questions into. Yeah, actually, well, I should yeah, I should put it here on the video so you can see. If you go to Handmade Network and there you go. Well, if you guys know or you don't know, Handmade Network is a community of developers that make awesome stuff. So yeah, I mean, here you can find a lot of projects that are related to code. You know, I guess most of them are related to code, and most of them have this idea of handmade. Make the things from scratch. So that's the philosophy behind this community, and I think that's awesome. Is pretty much the idea of EagleFly as well. So that's the reason I decided to put a post and make an account here, so everyone that is interested in this kind of stuff can see it. And if you are like new to this kind of thing, yeah, I mean, you can just dive into this and see all the projects that you can see here. There's for Coder, that is the editor that we use. This editor. This editor was made by Alan Webster, which is is a person. I mean, he started. He has the project listed here, his project, and there's also other awesome projects that are as well posted here. There's Handmade Hero. It's a video game that it's awesome because they teach you how to program. If you don't know how to program, you can go and follow that, which I believe it should be somewhere here. Yeah, here it is. And there's a lot of it. So yeah, I mean, I post here the thread, so let me show you here where I posted. Here you go. You can find it in work in progress. I don't know if I think you need to have an account here, so you can post, and you can see it without an account. But if you want to post your questions here, I think you need to have an account. So yeah, so this is another place you can follow me up. Here I will be uploading basically this front page with all the new things that we put. You can see here we have the output, the current output of it. This is just a little text that I put about the project. We have here the links to YouTube and Twitter. And yeah, you have any questions, you can post them here in this post. You can just put any one here, and yeah, or you as well, you can post them on YouTube or Twitter, and I'll be there to answer. So yeah, so let's start with this and open the project. And So if I compile, we are gonna see pretty much that we do run. I'm gonna open the debugger so we can see the output. And I can probably run it here, I guess. There you go. And if I run it, there you go. Come on. Here you go. So this is our current output on the console. As you can see, we have the same stream as we had before, and yeah, we didn't make any addition to the stream, but we were just making some changes to making some compression in the programming, which is the way that it should be. You know, it's the way that you can program faster and better. So yeah, and I mean the idea, I don't know if I already explained it or not, but I mean I think it would be nice to explain as well back, like what is compression oriented programming, or if you have never heard about it. It was Mr. Casey Muratori, the one that, well, at least I don't know if he was the first, but I learned it from him, and it was like, you can see here his post. Is the person that started the Handmade Hero project that I just showed you before. And the idea behind compression oriented programming is that you start writing the usage code first. You know, that's the first thing we did. You know, this is spaghetti thing that probably doesn't have a lot of semantics, and it can be like all these parts, and it doesn't have any accumulation into it. It's, you start by there, you know, and once you have something running and usable, and that's the word, usable, is when you start caring about how to compact all the stuff, you know. So first you elongate everything, you know, you see the whole thing, and once you have something that's running and usable, you start compacting everything semantically. And semantically, I mean that, you know, the things that relate to each other are gonna tend to be close to each other. You know, that's what semantics mean. As you can see here, I mean, one of the things we started doing with that semantic stuff is this. I can show in the code is better. We can see it into get mnemonic entry. If you see this call, before we have some spaghetti code that was push register name, and push register name is pretty much this thing called. So we got that and we put it into function, and now because we saw that this piece of code, you know, this function was used into places, you know, so we saw hey, well, we can compress that into one function, and it can be used by two places, you know, and that's pretty much what we did here, you know. So we push the register on fetch register open, and we push the register on get mnemonic entry. That's pretty much it. And you know, something else as well that we did, and that has to do with compression oriented programming, it's the whole idea of the stack, or the, I mean, in the first part here, you know, we have we haven't finished it yet, but we already started to have our own stack, you know. our own frame stack for putting and making each the decoding process for each instruction, you know. So each decoding process for each instruction is gonna have its own context, its own stack of flags, and it's just gonna iterate onto it. So that's the idea that we found, and we didn't find it at the first time when we were writing the usage code. We didn't know that, you know. That's important. We didn't know anything about even the code, how it's gonna how was it even gonna work, you know. We didn't know anything. And the important thing about compression in the programming is to pretty much explore, you know, explore doing the first thing you come to mind, you know, the first thing that comes to your mind. Just do it, just write it. If it works, well, you got it working. Once you got it working, you start compressing with different functions, different modules, as they call it, and that's it. You know, it's pretty simple. There's nothing more to it. And of course, I mean, sometimes it's gonna be a little bit difficult to think about how to compress semantically some code, but you know, it's all about experience. You know, it's all about discipline and doing this a lot of times. So you get like doing and doing and doing until you get it. You know, that's the whole point of it. Probably at the first time you're gonna just feel like what's he talking about, or it's gonna be a little bit harder to understand how to do it. But it's just about doing repetitive this stuff, you know, thinking about compression, and yeah, you know, I mean, it's all about that. And this is I mean, if you guys, I don't know if you know about object-oriented programming, but yeah, I mean, object-oriented programming is totally the opposite, you know. Object-oriented programming totally sucks. It doesn't follow this idea, and it's pretty much going in the other side, you know. It's totally upside down. So that's the reason why it's super difficult to program with object-oriented programming. And yeah, that's what I'm about to say. So with that said, with that inspirational thing about just trashing out object-oriented programming, we can start this. I feel better now, you know. Always trashing object-oriented programming is gonna be the thing, you know. If you trash object-oriented programming in your day, you're gonna feel better, believe me. You just have to try. Okay, so yeah, if we compile, yeah, we know it works, you know, pretty much the same. Now, I believe we left off something important, if not, well, I mean, I'm not gonna say it. I mean, we were doing it on the last part of the stream, I believe. We were changing we added these end instructions to the encoding and begin thing, which pretty much define the context, the context where we are going to work with. I'm sorry. And which, I mean, right now it's just like that. It's pretty basic. We just create a context. We didn't even initialize it. It's initialized to 0, and most of the time we just give it the base, you know, where it's going to start with, and we just move around. And the reason we did this is because and again, with compression-oriented programming, it semantically has the meaning, you know. When we saw the code, it's like, well, you know, I mean, well, at least myself, I was like thinking, well, you know, this looks a lot about like a frame stack, you know, or you know, we have a frame of reference where we start, where we end, you know, and we do this repeatedly, you know. That's the whole thing about a disassembler, you know. It has this semantic of what is working with on each piece of code, or in this case, of each piece of opcode, you know, and that's it, you know. I mean, it's nothing more to it. So we changed everything to be relative to the base, except for well, everything, most of it, let's say, is relative to the base, you know. If we see fetch register, well, except this call, okay. Except this call, and because that was that was the thing that we needed this, because since the bytes, how can I say, this needs always the mother and byte for it to work. So we didn't want a conflict for having the this to be adding bytes to the counter, let's say. So even though this doesn't care about it, and that's pretty much because of the nature of this call. The nature of this call is totally independent of the context of it. The context of the disassembler itself. So I mean, if you think about it, probably this in the future is going to collapse a little bit more because it's context independent. So the one that is totally context dependent is the fetch memory open. That's the place where it's pretty much the heart of the context. It's the one that controls how much bytes we pass by, where we put it and stuff like that. So the only thing that I want to change here is just here, where we say, hey, we have this. We don't need to do this anymore because we have the mother and byte. And that's it, I believe. And yeah, because we knew that we needed to have the mother and byte, because the mother and byte is used for a lot of things inside the context and the disassembler, so that every time that we need to pass it, we just need to use it, and that's it. Of course, this can be always moving around. That's why we have the I by count, and that's it. We just add the offset, and that's it. The way we add it, it all depends on whatever we push, whatever we find out to do, but that's it. So if we run it that way, so it's pretty much the same, see? Yeah, that's good. And something probably I want to mention right now is just like, I mean, right now the stream and the thing we're doing is super simple. We started up with, and that's good. That's important for us to have right now, something simple that we can read and compare against pretty much reading it. But probably in the future, whenever the streams become longer, we'll need to have a utility here where probably, I mean, what I was thinking about is to have like some kind of matcher, where we can start comparing this stream with other streams from other disassemblers for other decoders and stuff, so we can see how well did it did, and we can see percentages, we can see where did it match and stuff, we can have a matcher utility there, so we can see how different we do the things, and that is going to help a lot in the future whenever we start to really pushing this stuff and making it to the place where we are going to ship it and clean this stuff, whenever we see, oh, okay, we have the whole thing, the whole API working, and then we say, oh, okay, so now let's start. Well, I mean, we can start before or after, but I mean, once in that moment when we get the point where we feel like we can start testing this stuff against other decoders, we can just start by there and see and make a utility that makes the comparison, and yeah, it's something that it could be nice to do. So yeah. So now that we have that, you know, I think, and I don't know if any other place can use the modern by as well. Probably the fetch. No, how do you call it? Fetch immediate. The fetch immediate is going to work against the context bytecode, so we use the base, which is fine, I guess. It's not, because the resolution for it has to come from fetch memory operand, so this cannot come before or after. This cannot come before the fetch the fetch memory operand. Yeah, it has to come after this, after the fetch memory operand. So yeah. So yeah. So I think, I mean, without doing more like this kind of compression, I mean, we can do something about the file thing. You know, we are starting to have something that is starting to look a little bit big, which, well, it's not big, but we probably want to do something this with the file spec and start doing about something about that. But I think, yeah, it's still missing some data, you know. I mean, the best place, I think the best time to go into the rat hole of making the file spec, it's gonna be whenever we feel confident that we have pretty much the API working out, you know, all the things they need, the way they need it. That's the way this has to work. If we don't have the other thing working, we are just gonna play around, not knowing what do we need about the file spec, you know. So that's why this has to be one of the last things we do. It can be pretty much the same at the same moment in time when we start to make the matching, you know, and all that stuff. So yeah, I mean, we can leave that outside of the thinking right now, and we can try to make another disassembly thing, you know, because why not? I don't know if we can compress something more. We haven't tested this yet. We have to do this. Where is it? You know, 66 overrides, something like that, or all the prefixes that are possible in the life. So we have it, and we have it here, like operand size override prefix, but of course, you know, the operand size override prefix has to come before the array_x prefix, you know. So it has to be checked. Well, it can be checked whenever we check it afterwards. That's not the problem. It can be done right there, but we have to think. We can start thinking about prefixes, you know. I don't know what should be the best thing to do now. I mean, adding more instructions, of course, is gonna help. We have such a little thing. We haven't done a lot with the pushes. We just added it like that. So we have programming with general purpose. I wanna what is this? shall we start to do the call and stuff like that? You know what I mean? Or jumps, conditionals. We haven't tested conditionals. We don't have any conditionals, isn't it? We can do conditionals or the call. Let me, we can start to think about jumps. We haven't done anything about jumps in a while. Well, we haven't done anything about jumps, so let me put the charger. Hold me a second. All right. Calling, interrupts and exceptions. So the thing I was like thinking, let me find. Since right now, if you remember, we haven't done anything about floating point data encoding. We just like encode the thing and we just upload it. We can do that as well. Since we already like kind of pinhole there. We can do that. And try to expand the idea of encoding, because it has a real encoding. It's not just right now we just have it like super janky there, so we can do that. Well, you know what? Let's go and make call. Let's go and make call. And I believe, I mean, it's better, well, it's simpler to make the jump than the call, isn't it? So first let's do the jump. Let's do the jump first. The address can be a relative address or an absolute address. Okay, that's important. That's important to understand. Relative and absolute addresses. So let me put it here. And you know, the nice thing about jump instructions and transfer control program is that it's gonna guide us to the next thing that we want to do. Well, a thing that we haven't done yet, and is to add proper addresses of stuff, you know, like having the addresses. It's important, you know, like to think about addressing and where are we looking for, you know, like it's a relative address. Okay, look forward to this, you know, it's a, and that's, it poses a question about, well, how do we want to do this? If we still want to do this and have like the computation, you know, like this means this address, you know, which, I mean, okay, the simplest way to see it is just like, oh, we made the computation, instead of printing this out, we just print the result value, you know, which is normally what disassemblers do, you know. Most of the time when you see a disassembler, you're gonna see computed values from here, you know, so you're not seeing this stuff, but you're seeing the computed values. So it can be yeah, I mean, because most of the time is more useful to think about which is the address that we're trying to find out, you know. So jump to what? Jump to this address, you know. But sometimes it's nice to have the registers as well, you know, because the registers have the the path trace, you know. If you see the registers, you see, oh, okay, so you're using these registers to make the path trace. That's why you push, that's why you move I don't know, this immediate to this R13, so that we can just use that for addressing, for an addressing mode, you know. And it's like you have a better idea of what's going on, because if everything is compressed, you will have that problem. Of course, you want to have, it's like having both images, you know, the expanded image and the compressed image. Yeah. So I mean, I can see like having the expansion and the compression here somehow, like just one by one uh, one aside the other. Yeah, it can be. It can be. I don't know. We can explore there. Okay, so the offset, which is a pointer, um, is the one that goes on the EIP register, and the CS of the segment selector, sorry, goes to the CS register. In protected mode, the jump instruction also allows jumps to call gate, a task gate, and a test segment. Okay, that's important. So if you think about it, absolute addresses cannot be immediates. I don't know. That's what I am thinking about. But we have to make sure about it. We have to find out. We have registers for absolute addresses or using the standard addressing modes for the processor. Now when it's a register, it can only be a near pointer. Equally here. I'm sorry. Or if it is an address using the standard addressing modes, which it can be a register as well, isn't it? I don't know why that. Actually, I don't know what they mean by standard addressing modes. It's something that we have to find out. So let's try to find it out. Okay, I was like, what? This is the AT&T syntax. Okay. We can only add register values. And we can have only two, yeah, one in the base, one in the index. We know that. Okay, okay. So that's the reason why we have by pointer, word pointer, and door pointer. Because if not, it would be pretty much weird to see the immediate thing. It's like, whoa, what are you looking at? A byte, a word, door. So that's important to add as well. Mm-mm. So that's interesting, because the syntax, when you see assembly, and this is special because normally, we dereference value in the memory whenever we want to, let's say, move the value from some place in address onto the register. For load effective address, it's the other way around. We don't care about the value, the reference. We just care about the address value that we are computing. We still have to put the brackets for it to understand that it's at memory, you know. But it's unnecessary probably, because we know that it's we just care about the value. We just care about the address. But yeah. This arrow should be the other way around. We store on ESI. So well, okay. Boom, 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 boom. Okay, he first pushes EVP, move EVP SP, so he's growing, moving the base pointer to the stack pointer, then the stack pointer is moving by 4, and the top of the stack is being with the EVP, then it pushes ADI, so since we push 2 4 byte EDI, 2 4 byte registers, EDI ESI, we have to move from EVP, which is pointing to the, it has the stack frame, plus 8, it moved from EAX. Oh, okay, but ESP has been moved 4, then 4 4. I don't remember. Let me think. Yeah, this is not, this is better. And we can see it, we have a good thing for that. They are the stacks. Now right now we don't care about that too much, so yeah, I mean we can check that later. So we're just gonna disassemble a jump instruction, a simple jump instruction. Okay, so let's try to find a jump instruction. There we go. So we have all these jump instructions. Let's try to do a relative one, you know, that has a jump short, which is from RIP equal RIP plus AP displacement and extended to 64 bits. Yeah, we can start by that one. Those are all these are near and these are far. Okay, so let's start with a near thing. Let's start with a near thing. This is kind of nice. We can just do this one. So we have EBCB. That means that we have a byte, you know. So we can even use the test asm and try to see how can we do that. If we say jump, do we have a CB? Yeah, we have this. Alright. and the test action is telling us that invalid operand size for instruction. That means that you cannot have that. Okay, so since it's a relative, it has to be a displacement. It's a D. It just has one operand, and it not applicable, not applicable, not applicable. And the other is mother RM field. So it's just an offset, so it has to be jump say you have like that. Okay, so jump code. We can't put a label, isn't it? Okay, so we can just say block. There you go. There you go. I don't know if this is gonna be the one that we want to, but since it's a near call, so it has to be near. It can be any one of these. So it can be this is not supported in 64. Jump near relative RIP equal RIP plus 32 bits. Display is extended to 64 bits. Okay. And probably this is the one that we're gonna find. We're not gonna find the EB one. But jump near absolute indirect address 0 extended. I'm sorry. We have jump near absolute indirect address this is an absolute. Okay, it comes from the RM16, not supported in 64-bit mode. Okay, this is a jump near absolute indirect address given in not supported in 64-bit mode. Okay, so if we if we disassemble this, and we call, how do you call this? Don't bind disassemble. Oh, my bad. There you go. Okay. So yeah, we have a bunch of pushes, adds, FL, jumps. Okay, so yeah, here's the jump. So yeah, it's a B. It's a B, perfect. EB6. So we can even encode this, you know. Okay. Perfect. Now we have to think and make sure that E6 it's an AB displacement. That means that this thing is gonna be sign extended, you know. It's added to 40106. So if we make the calculation should gets us to E6. So the offset to jump, we can even make it simpler, I guess. Well, it's just that these instructions have to move to until the move, you know. And probably yeah, that's possible because it's just is less than something. So let me move this a little bit. So let's say we just move one instruction back, you know, so we can see it a little bit simpler. So yeah, EB effect now. Now we're jumping towards 40164, which is this one. So that means that we are moving from this F8, but F8 here's moving 1 to A. Okay, 1 2 3 4. Well, we're moving 1 2 3 4 5 6 7 8 bytes. Oh, and it's negative, isn't it? Well, yeah, it's negative, so that's why it's F8. So if we see F8, effect, it's well, its value as a negative number, it's something like -1, -2, -3, -4, -5, -6, -7. Oh, we can do it here. Let me do it. We'll have 1 1 1 1 1 1 0 0 0, and we have 0 0 1 . So I have to say -1. That means that I have 1 0 1 1 1 1 1 1, and then not 0 0 0 0 1 0 0 0. So yeah, 1 2 4 8. So this is equal plus A, and this is minus A. So F8 is -8. And I was just making the operation, the subtraction, you know, because I was like thinking, well, what number is it, you know, and I just changed it to positive. I can put here. I don't know if you see these guys, okay? I was gonna just put that, but it's just super simple. But if you want to know, This is the way that, and let me see if this is done correctly. No. No, this is gonna be impossible. No, forget it. Okay, so yeah, I'm gonna do it with that. Okay, with Mr. Where is the Mr.? I don't know where we put it. It was Milton. So I'm going to write here, you know. So oh my god, tools view. So here you go. So we have -8 that we didn't know that it was a -8, but you know. And for knowing that it's -8, what I did, it was just to convert it to a positive number. At probably, I mean, if you know negative numbers, well, that's gonna be okay. But this is the way I did it. So for making a positive number from a negative number, just have to -1. You know, you have to make this operation, which basically gives you, you know, it's just a normal operation but in binary. Okay, so we just have to say, oh, okay, so we have to carry, you know, we have to borrow, sorry, from the least significant bit set and set all the bits before that, and then we can just say, well, you know, I'm gonna set the others as they are, yeah, and once I subtract -1, I just have to basically not them, yeah. So I'm gonna say this, and then I'm gonna say this, and then I'm gonna say this, and then this. No, we just change the value from 0s to 1 and from 1s to 0s. That's what this not operation makes. And if you guys know positive number values as I do, you can see that this is equal to 8. That means that this value is -8. Okay, that's what I did in here. So yeah, I just want to explain everything that I do so you guys can know. So if we know that makes sense, you know, because we have a -8, because we have to move, you know, where is it? No, we have to move from jump. So this is 1, 2, 3, 4, 5, 6, but remember that we are passed by the instruction. So that means that whenever we execute instruction, the instruction pointer is going to be already on the next instruction, you know, because it's one ahead. Remember, the instruction pointer is one ahead of the instruction executing, of the instruction that the processor it's executing in the moment. So the instruction pointer, it's here, you know, it's on 10C6C, and it has to come back 8 bytes, you know, it's -8. 1, 2, 3, 4, 5, 6, 7, 8. And then it goes -8, and then so that the next instruction pointer can be put there, you know. So the instruction pointer is going to be I mean, the EIP register is going to be modified with this value, you know, basically. So this value, which is this value right here, is the same, you know. Is this instruction? Yeah, we want to move to that instruction. That means that the EIP value has to be loaded with that value, you know, explicitly. And that's the way we go. So we can just do this simple instruction. It's super simple. in this case, probably, I mean, our instruction string doesn't make sense at all. You know, it's not a it's not a program. You know, it's just gonna make not sense, because if you think about it, I mean, you can put that instead of moving f8, I move 4 bytes, let's say, you know, and then you will move to something that's not the instruction that we executed. So the decoder for the instruction set is just gonna do bananas, you know, because it's gonna think that the instruction is something totally different. Let's say we move 1, 2, 3, 4, 5 bytes, you know, and we say that the instruction pointer starts at 2f. So 2f is just a different instruction, you know. So we have to the disassembler has to be really careful about that, and ourselves as well, you know. It's just like we cannot just, I mean, and the reason is because we have the possibility to have that kind of weird movement that we don't want to do because of unexpected behavior that could happen with the processor. It's just that it's gonna break the instruction stream totally, you know. It's like reading the instructions, looking at them, and it's just like what's going on here, you know. So yeah, something to make sure. So let's copy this and to the instruction stream, just for making this fast. I'm gonna put it on the CPP as our instruction stream. And there you go. So we compile that. And right now if we run it, it's just gonna be bananas, you know. It's not gonna think nothing about it. It's just gonna say what's going on here. Oh, hold on a second. He thought it was a move ET1 to EAX, which by no means it is, you know. It's not bad, you know. So yeah, and the reason is because we haven't added that code, so we should it. So let's do that, okay? So first thing to do, let's copy this onto the instruction string, data information. For doing that, I would like to see first of all, this instruction should be a 1 byte thing, you know. I don't see the reason why it shouldn't. So if we go to EB, it should be here. No, ish, where is it? Yeah, here. Yeah, we are here, E, and we are looking at this one, at the short GP. Oh my god. This is an interesting instruction because the operand size is forced to a 64-bit operand size when in 64-bit mode. Prefixes that change operand size are ignored for this instruction. That means, okay, that means the prefixes that change operand size are ignored for the instruction. So what does it mean that, so what would happen if we are in 32-bit mode, you know? Because the instruction itself, oh, I mean, it's valid on compatibility mode. but the displacement is also sign extended to 64 bits. No, it is not, isn't it? I mean, this is not complete, this thing. It should be when on 64-bit mode, because if we are not on 64-bit mode, it's gonna be 32 bits, you know? Or at least it should. Let me see. Refer to a different point instruction string without recording, return information, destination target. Operand specifies the address of the instruction being jumped to. This operand can be an immediate value general purpose for memory location. This instruction can be used to execute 4 different types of jumps. Near jump to instruction within the current code segment. The segment currently pointed to by the CS register, sometimes referred to as an intra-segment jump. A near jump is cool. A short jump, a near jump where the jump range is limited to -128 to +127. Oh, okay. From the current EIP value, okay? That's the instruction that we are decoding right now, you know? That's a short jump. A far jump, so it can be just -128 to +127, you know? So he doesn't care about the code segment at all. So probably that assumes some craziness going on there. So if we are on, let's say we are on 0, you know, the code segment, and we just go negative minus something, then we'll just go to another code segment and it would be bananas, you know, like what's going on here. But I don't think so, because look, it says a near jump, so yeah, it gets respected that it's a near jump, but it's a short near jump, okay? A far jump is a jump to an instruction located in a different segment than the current code segment, but at the same privilege level, sometimes referred to as an inter-segment jump. Okay, that means, okay, so we cannot change to another privilege level unless we use a task switch, or unless we use a gate. Yeah, remember gates? Yeah. So yeah, task switch. A jump to an instruction located in a different task. Okay, we need a task switch for that. Okay, we haven't seen that as an example, but we have seen what happens when making task switches and stuff like that. So it's not different from that. You just have to see an example. A task switch can only be executed in protected mode. See Chapter 7 in Intel 64 and FAQ architectures of the developer's manual. Voluntary for information, performing task switches with the jump instruction. Near and sharp jumps. When executing a near jump, the processor jumps to the address. When executing a near jump, the processor jumps to the address within the current code segment. An absolute is specified indirectly in a general purpose register or a memory location, RM16 or RM32. The operand size attribute determines the size of the target operand, 16 or 32 bits. Yeah. opcode for short versus near jumps and the operand size attribute for near relative jumps determines the size of the target operand. Yeah. Oh, okay, I got you. This was like a target open. What's the target open? Yeah, the value that's, if it, in this case, the immediate for the 8-bit, which is then extended to 64. For jumps in real address or virtual area, okay. Okay, so I'm gonna, for jumps in protected mode, let me see. In 64, the instructions operation size is fixed at 64. If a selector points to gate, then RP equals to 64-bit displacement taken from gate. Else RP equals to 0 extended up from the far point of reference to see this summary chart at the beginning of this section for including data limits. Okay. If near a jump, and this is okay. It's like what? Okay. Okay. I got you. So yeah, it's forced to 64-bit mode. It's forced to 32-bit mode. Yeah. So we have to have that representation as well. So I'm gonna let me remember, we normally add it on the bottom just as a stack. So let's push another instruction here, which is called jump entry, and it doesn't have a mother m, so that's false. It has a rectum mother m, that's false. The register operand size, it's gonna be it's not defective, it's 64-bit in 64-bit mode, so it's more like we have an operating mode, you know. We can use that. We can use this one, yeah. The others probably not, but yeah, this is more like we want. It's forced to 64-bit mode, or it's forced to 32-bit mode. You know, that's what we're thinking here. You know, so yeah. So operand count, it's pretty much 1. Mnemonic name, string length, it's a jump string, which we can add, of course. And we have operation mode. Yeah, it's valid on both in 64 and 32. And we have the rect type. It's well, actually I'm missing something, the immediate size, so this is more important. We have the modern present, rectangular rect field inside, it's false, so we don't care about that. Operand count. Yeah, we have that. Register operand size. We have register operand size, so it's invalid. The immediate size, yeah, we don't care about this. It's a data size. 8-bit. Okay. Yep. Mnemonic operation mode. And we have a rect type. What's the rect type? Or why do we use it? Why do we use this thing? Oh, okay. We use the rect type for choosing between normal stuff, you know. So we don't have a rect type in this case. We can just default to the normal thing. And yeah. 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 Yeah, I think so. Yeah, why not? It's because, well, we have rect type in there, then we have rect type in the get mnemonic as well for them. We have rect type. We have XMMM, GPR. Normally, since it's default to GPR, that's why we haven't used it. We just change it whenever we have XMMM. So my question is, which types do we have? We have GPR, MMX, XMMM, control, debug, FP, and UI. Okay. Yeah, because that's the table that we have for the register thing. So yeah, that's fine. So we have GPR. We don't care at all about that. So it's nullified. So we can just say that we are going to say it's important to, well, in this case, yeah. I'm sorry. So why do we have all these? Okay. So yeah, we don't care about that. So let's change this to be that. And this is the same. And the rect type, yeah, it can be GPR. It doesn't matter. We don't care about that. We don't care about that because we are not getting GPRs at all. So it can be invalid, you know. Yeah. Right. And right, well, let me first jump to the jump string. Here I'm gonna say that this is jump, and then I'm gonna say as well that we have another one to the one variable table, and we need to add it here as well. There we go, we have EV, and there you go. Right, so let's see what happens. we don't know what's gonna happen, but we can see, right? So we have C by, you know, it's EB, that's correct. And we start picking the operand instruction we got from the base, that's correct. And we don't have any REX prefixes, so we're just gonna assert that everything got it, you know, we got the table. We have modern map set, yeah, we have it, but we don't care at all by that because we have it. So we have the get entry index, and the context entry is gonna be a move. It's still a move, as it seems, which is a little bit weird. Have you repeated it? Are we adding it correctly? That would be my guess. I don't know, but we don't have to guess, we have to find it. So we have a jump here. We have GPR. We don't have a move. We have a move? What kind of move do we have? We have a move. Well, we don't have many moves, isn't it? Well, we have 3. We have 3 moves. All the moves are, well, let me put move. We have 3 moves there, 3 moves, and yeah, we just have 3 moves, which are on the same code, but none of them have 2 pushes, we have jumps. That probably means that this is already busted. So let's see. Let me compile it back again. This is all data that we got before. So let me put a breakpoint into the initializer so I can see that we properly are doing this stuff. I wanna put AB, probably is because the get entry index is just busted. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's correct. So it should match. So let's put a breakpoint here. Guess. Okay. it didn't put the breakpoint on. One more time. Put the breakpoint, please. It didn't put the breakpoint. Oh no, okay, yeah. So we go into here, there we go. So we see the disassemble table. So the 9th is this one. This is a push. Okay. No, yeah, this is the 9th. So here's the jump. So isn't this busted? Because this should be 1, isn't it? Unless we take out the null entry, which I don't know. No, we still have the null entry. So this is busted, isn't it? This should be 1. This should be 1. And the out by index issues here. The interesting thing here is, since we use it here, yeah, that's, well, at first, if we wanna match that thing, I don't know why we haven't done this. Well, because I don't want to have the 0, 0 because that's a valid thing. So I just want a null entry, you know. So the thing that we were doing here before is just totally busted. Let's change that. So if I move here and I put get entry index, we already know we haven't erased this stuff. We still have this kind of crazy thing, which we don't need anymore, so we can probably erase that. So let's do that now. Okay, so I'll erase that. And I'm gonna do here whatever. So I'm gonna, let's say we have to collapse that part. I'm gonna say this. So let's just open all this stuff. And later we're gonna collapse it back again if we see the need. Yeah, because it was a little bit hard to think about that. So yeah, this is gonna be different. So the mnemonic count is not used here. We use the total entry count to be adding. So that means on the disassemble we have, where is it? Disassemble. Yeah, we have two counts here, yeah. Total entry count, which comes here, and then the mnemonic count. which is not what we want, you know. In fact, I don't know where else do we use mnemonic count at all. Is that all? So yeah, we can just say goodbye to them. And here ID is gonna be something totally different. Here we're gonna say that the ID, how do you call this? Of bytes. Of by index. Here you go. And that's all we gotta do there. And this is and well, we can do that. And then we can just say, well, you know, index is equal to so we just match the same thing. We have a null mnemonic count, and in that way we will always be pushing forward, you know. Now, well, this is not possible because up by count is just, it has to be entry index plus or group up by count. In that way, it's just gonna work. Yeah. Or well, I can just move it back. Just to keep it simple. And we just keep it that way. You know. Entry index, up by entry index. And that's it. And here we don't need this anymore. In fact, we can just say that we just inline that part. And well, I'm gonna keep it here. We have index, group up by count, index, up by entries. We are just making linear search, so we can just say I don't remember how we were doing this. Okay. So I don't know why do we use the base somewhere? Oh, but we use it for something else. So yeah, something there. What? Okay. So we need to also add the base as well. So for here, I'm gonna go to initialize on the lowest border, and we need the base, of course. Oh, I call it first byte of index. Okay. So what was that? This is not called first byte index. EagleFly up table group. Oh, this is register group. Oh, my bad. Okay. We need a table group. Table group. Here you go. So you see here, where is it? These two, well, they don't look pretty much the same, but we can start compressing all this stuff as well. So this is gonna be damn. Oh, my bad. What am I doing? Here. This is like this. And I don't know what we were doing here, but we just need that. And just say, hey, you know, we have entry, we got the index, and we don't need to do that. If id equal by entry id, we break result, and this is gonna be index by entry index. Yeah. Yeah. Now this ID is gonna be a table, how you call it here, main of by, what's called? Table main of by. I don't remember. Yes, I guess. We may not buy whatever. Sometimes it's gonna be the mod RAM, sometimes it's gonna be, but yeah. So it all depends, isn't it? It depends on the group, which is the data that we are looking for. That was the reason why we were like doing that kind of craziness. But we don't need that. We can make a change. If we compile this and we solve the problems, okay. So we're just gonna, we don't need that anymore. I'm just gonna do that like that. And so we have these two, okay? So we're gonna need these two. There we go. So we are not doing anything fancy there, you know, it's just like we're just doing the thing we find possible to do. And then we can just think of something better to do. So this is not needed. Get mnemonic. Here we go. And this is just the thing we want. So we want to assert here. We cannot assert, but we can say well, we can do that way, I guess. Now this is gonna be a caveat. I mean, well, I'm gonna run it just to show you that this is not gonna work at all. And the reason is that, well, if I initialize, this thing is gonna work. If I run step into the next, I can just step into them. And let me first check if this happens to work. And we're gonna say up by entries. We have 3-1. Then we have 5-2, 62-3, 89-4, AB 88, 50, 4, EB. And then on the next one, A4, F, C3, CC, 40, 405, E1. Okay, so this seems to be working. We're on group index. We don't have a lot of group indices. We just have 6. That's good. So I can just step outside the code and say, well, you know, let's go. It seems to be initialized properly. So let's see what happens. Probably the first one is going to work. Probably, I don't know. And we got table ID. Which is 1 byte of table. That's correct. So we're just gonna iterate through the out by entries, you know, and well, C by plus main of offset is EB. And it didn't enter at all. It didn't enter. Oh, my bad. Yeah, I had a bug. I get a bug. Yeah, because we're saying here up by index. Yeah, this is this we're using a lot. I mean, we are using the null entry. but this should be entry index, and then entry index stars, and we just keep adding, you know, all the indices. So the indices should be matching, you know, the out by entries, just 1, 2, 3, 4, 5, and the out by indices has its own record. So that's the problem. One more time. 5, see there, 5, so first out by index is 1, that's correct. And that's why we didn't get the entry index, because since it's the last one and we just finished one before the one that we were looking for, that's why we didn't get it. So I can just step down and let's see what happens now. So it should be the last one, yeah. We have, how many we have? We have 9. So on the 8th, and we didn't get it at all. That's something weird. So let me see. We have this as a mistake here. So the up by entries, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and the 9th is the entry, you know. And then we have A, B, C, D, blah blah blah. So how many counts do we have? 9. 1, 2. Oh, because we're looking to the, well, yeah, it should be, isn't it? We are on EB. EB. What's going on? Okay, one more time. One more time. One more time. Oh, okay, I see the problem. It's like, oh, okay, we start on up by index, but it has to be first by up index. Okay, my bad, my bad. So yeah, the same problem, not solved. Group first byte of index plus group of backend. My bad, my bad. My bad, my bad. Continue.
So now we should get it. (8A) 5054 EB. There you go. You get the entry index, and the entry is a jump. That's correct. And we don't have a rec field inside. That means that we are not gonna get it there. And we gotta fetch a memory operand. We don't have it, so just say that the byte count, we don't add it at all. And then we have a fetch register operand. We don't have it, so we should just say here that we don't do anything at all. We have an operating mode. Okay, we have fetch memory operand. It's blah. That's correct. For blah blah blah, push string to buffer. And right now we don't say extend this one, isn't it? Okay. So the buffer is just gonna have the F8. And there you go. So now we print the F8 correctly. T byte now it's pointing to 41. That's correct. So if we see now, if I run this continuously and just there you go, that's a problem. Where is it? Let's see the match, so I can show you the caveat. So we have push R12, push REX, move SPL REX, move RBX R13 REX and stu, move RBX RBP REX and stu, move RBX RBP REX times 1, move RBX RAX times 4 plus blah blah blah, move RBP RSP plus R12 times A 0033221100, move R8 core R12 R13 blah blah blah, R8 RAX RAD RAX RAX RDX RAX this NAT RAX FFF0 OB FAT ST0 ST1 FUCOM ST1 ST0 FLD blah 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 BM resume Line RX XM0 XM1 shield left double EAX03 at EAX000. So that's kind of weird, since how can I say, I supposedly thought that we would have trouble looking at the thing. Probably, I don't know if we already have changed that, because well, in any case, we will need to have it that way. The thing that was like, let me see. I mean, since some of the encodings here, and you see here, this on the bottom has the mother and byte encoded, that means that we have to look for those mother and bytes in the encoding itself, which I thought we were not doing that before. So if we go to the CPP here as well and go to the get table ID, It should be for the abstention table, I guess. Yeah, these ones. So yeah, I think, yeah, we are doing it. Look at this. We are setting the main up offset the same as the motherm offset. So this function is already solving the problem that we could have, because we are just making sure that we are not looking at the main of by, but we are looking at the motherm by. So yeah, that was the thing I wanted to do now, but since we already are doing it, that's why it's doing it correctly. And now we have null entries there because we didn't find that entry, so we print all nulls, which of course is a little bit weird, but that's correct. So yeah, that's it. Oh, and let's just sign extend this, so we can just do the same thing. So let's do that. So let's go to fetch. Oh, okay. Fetch memory open, and right here we have a sign extension code, which is all this, and we are gonna do, in the fetch immediate, we have to do the same here. So I'm gonna copy this and say this is the same as this part here, and context up cam, and then here is the value. So we basically have to copy this. And we don't care about that. And here we have to care about, this is a little bit different. This is entry well, we have the immediate size, isn't it? That means that well, we have it on the immediate size. I don't know. Initialize. No, we have on the register open size. Yeah, I don't know why we have it on the register open size. It's not a register. It should be so we have to do something similar to the fetcher memory operand, where we normally we don't sign extend. Well, we haven't thought about sign extending immediate, so all the immediates that we have right now, we just print it out. We don't do anything at all with that. But this is a special case because the data that it's an immediate has to be sign extended. We can do it as well. by having here some data information, you know. So we're gonna have a unit32 immediate operand size equal data size is gonna be, well, we have it here, isn't it? Context entry immediate size. Entry So I like this because this is telling me what's the size of the thing. For displacements, it's on the mod RAM. They're gonna tell you 32-bit stuff like that. For this, we want to have one that's gonna tell us how to fit. This is the other way around. The immediate size is gonna tell us the size, and we have to have another data information that has to force the thing to be 64-bit, you know. So that's why we are doing register using the register operand size, but I don't know what to do here. We can add just another thing to the entry that says, which is the default thing here, I mean, which is the size. Since this is a jump instruction, it means that we have to load an address, you know. The size of the thing encoded, it's 1 byte, so that's okay, you know. The immediate operand size is 1 byte, so that's a thing. But we want to sign extend it to another size, you know. So normally immediates are sign extended if we have the S bit flag set on the encoding. If we don't, then we don't sign extend. So that means so there was a place where we were using that's not sufficient, and get mnemonic we have this thing. Effective operand size, system state, operation mode. Where is it? Yeah, here. this is because this is a register. And the jump itself, if you see here, it's not like he didn't put the brackets. And that's because you just put in the address. Normally it would be a label, but he didn't put the label at all while the disassembler. I'm sorry. So we can have, for now I think we can use the register, but of course, I mean, it's not like semantically, it's not the data information that we want, because what happens if we want to jump, if we have to have some extension on the immediate and some extension on the other. If that's the case, we will need another variable, you know. And you know, normally another thing that we can do for now, it's not going to be like a rule for something. Sometimes it's not, but you know, it's like you go to get index entry. Let me see. No, fetch immediate. Keep going. One thing we can do is now we don't have 32-bit immediates, or we do. We don't understand it. No, we just have 8 immediates, which is a little bit weird, but yeah. Well, I'm gonna use the register operand size, I guess. For now, it's totally junky, I know, but later we're gonna change it. And Okay. Now I don't know why we do this. We can just so let's see what happens. Okay, probably that was too fast. There you go. It has an extension. And we have an extension for this one as well. And the reason is that PLINR has probably something like that for the open. Yeah, because we're doing it incorrectly. Yeah. So yeah, we probably want another data information there for the immediate thing. Yeah. So that it's not just like, oh, you know. Yeah. Okay, so let's do it. Why not? I mean, probably it's just the only one that's gonna use it, but well, it's not the only one, but we need that entry. So I'm gonna put the tables and mnemonic. Here you go. We have immediate size, memory operand size, and register operand size. You know, and immediate size needs another EagleFly data size thing where we have effective immediate size. You know, that's what we want. And that's it. So if we want to do that, then right here in the immediate here is that we have immediate operand size and effective immediate, it's called like that. Oh, there, immediate size and we call it im size, well, whatever. Effective im size, whatever. Well, I'm gonna call it operand because it can be, it's an immediate, but it's an whatever. Yeah, that's okay. So yeah, that's the change. And of course we have to set it on the initialization pointer, so that on the entry itself we're gonna have another that is gonna be here. If in mid size, it's gonna be data size operating mode, and this is data size invalid. You know, we can just erase it. We don't care about it. We don't care about that. And there you go. Now we can just compile back again and see what happens. There we go, a bunch of nulls now. And then there you go. We got back our string as we got it before.
And yeah, I think that's good for today, you know. But hey, now we have another instruction, simple instruction, but we are just playing around with this thing that we have here. I think one of the next things that we're gonna do is to start adding the a fake offset, so we can just play around that. I don't know if we want to get rid of this, but you know, probably we can have another string that brings it in the way that it should, you know, making the computations themselves, you know, for the addresses. But you know, we will see. For now, please, if you have any questions, post them on Twitter or YouTube or on the Handmade Network. As I said at the beginning of the stream, I have a thread there. I have a post where I put them, if I believe I can show you back again where I am. This is the thread that I posted on the Handmade Network for an explanation of what the Handmade Network is for. Please look at the beginning of the video where I explain this thing. But basically you can see here, I mean, this is the an introduction to the project itself. This is the thing, the output that we see right now on the stream. Well, this is the last one, and we have pretty much the basic. Here you can post your questions if you have any, and I will be there to answer. Yeah, so please, make your questions relative to the thing we made today. And yeah, with that said, I would say thank you very much for coming, and I will see you all on the next stream. Thank you, and take care.